This is Engineer Samuel Sapi. So in this video, we'll be looking at basically how to go about solving the problem that is at hand. So before we begin, do not forget to like and subscribe to the channel. Okay, so the question says, determine the reactions on the beam. Now, before we even solve the question, let us understand firstly what beams are. So every time we're talking about beams, we're talking about structure elements that are loaded transversely, meaning the forces act perpendicular to their longitudinal axis. What I'm trying to say is that beams can be subjected to various types of loads. That includes, for instance, you could have a beam, say a simply supported beam, like that, and it could have a load such as a point load of W1. This point load is sometimes referred to as a concentrated force. And other type of loadings that these beams might be subjected to are, for instance, the UDLs, which are the uniformly distributed loads, as you can see in the question at hand. And when it comes to you analyzing these type of questions where you have to determine the reaction, you will be given more information. For instance, we've been told the supports at B, or so rather the support at B can be assumed to be a roller. Now, the support types, when it comes to beams, can be supported in different ways, such as simply supported, where you have two supports, or a cantilevered, where you have one fixed end, or fixed, where both ends are fixed. Now, with that much being said, we can start to solve this question. Now, looking at the schematic of the diagram, as you can see, we have two shapes. The span from A to this section here shows a dimension of 4. And the span from where I have sectioned here to B also shows a span of 4. Now, these UDLs we have here in section A, we have a rectangular distributed load, and at section B, we have a triangular distributed load. Now, before drawing a free body diagram, we need to replace these distributed loads with resultant forces. For UDLs, always remember to replace the loads with a single force equal to the total load. And this will always be the area under the load distributed curve. And then once you do that, all you have to do is to locate the centroid of the load distribution. So what I'm trying to say is this. Let's say we collect data. Our focus is on section A. Now, A is rectangular. And for rectangular distributed loads, we can always find the concentrated load, or rather, in this case, what we're saying as a point load, which we're just creating as a total of everything we're having. So we can say section A, we can convert the concentrated load, the distributed load into a point load, where we find the area of a rectangle, which is L by B. The length is 4, and the breadth will be 30. Now, with that being at hand, we can just apply algebra, and we know the value of 4 times 30. 4 times 30 will give us a value of 120. So we have a point load of 120 kilonewtons. The centroid, which is just basically the center, will be at L over 2. And the span is 4 over 2, giving us a value of 2 meters, just like that. Now, moving on to the other uniform distributed load, which is triangular in this case, we can say section B. In section B, the triangular distributed load can be converted to a point load by finding the area of a triangle, which is half base height. So we have half, the base is 4, and the height is 30. This gives us a value of 60 kilonewtons. And we need to place this 60 kilonewtons at the centroid of L over 3. And the value of L is 4, and this divided by 3 will give us about 1.33 meters. Now, every time you find the centroid of a triangular distributed load, be mindful, every time we use the value of L over 3, always start by moving from the highest peak going to the lowest peak, which means that we're moving from this portion here going in that direction. Now that these have been condensed to things that can be easily understood, let us now construct what we call our free body diagram. Now, the FBD is a graphical representation of the beam showing all external forces acting on it. This includes loads and support reactions. Now, moving on to the structure of an FBD, we're going to be having the FBD, in this case, as this. So we're having the reactions at A and the reactions at B. So the reaction at A, this is what we call a pin support. Pin supports will have reactions in the Y, so we have A in the Y, and in the X, so we have A in the X. Now I've been told that support at B can be assumed to be a roller. So at B, we have the reaction BY. Rollers only act in the y-axis. Now section A, remember, the position from A to the centroid of the rectangular distributed load we've calculated rather to say it's 2 meters. So we're going to be positioning the centroid of the point load of the rectangular distributed load at position 2 meters from A. And this point load is 120 kilonewtons. Now, looking at the schematic, we can try and draw this in a sense whereby we understand the dimensions in question. We know that from A to where the section here is, where the shape changes, the span is 4. So which means that here we'll have 2. Now from this point where the uniform distributed load changes its shape, we need to place the point load of section B at the dimension of 1.33 from the highest peak, which is in this direction, like I was saying earlier on. So I'm going to be positioning the 60 kilonewtons at position 1.33. This means that the span at this portion will now be 2 plus 1.33, which is 3.33. Now from the centroid of the triangular distributed load to position B, the span remains to be 2.67. Now the 2.67 comes about when we subtract 1.33 from 4. Now that we have this free body diagram, we can now apply the equilibrium equations. So let's now do a global equilibrium check. So the first thing we're supposed to do is to sum up the forces. We know that this is a static structure, and static structures, we know that the sum of all forces should amount to 0. So now we're going to say the sum of forces in the x-axis, taking this direction to be positive, should give us 0. The forces we have in the x-axis, we have A in the x alone. So this is basically 0 kilonewtons. And now that's our value for the first reaction at A. Then we do sum of forces in the y, taking this sense to be positive, which should give us 0. In the y-axis, we have the first portion, which is AY. If we start from A going to B, we have AY. We have 120 pointing downwards, so that's negative 120. We have 60 pointing downwards, so that's negative 60. And we have BY pointing upwards, that's plus BY. And the sum should give us what? 0. Applying algebra, we can create an equation in a sense where we say ay plus by will now be equivalent to, if we do the math right here, it's 120 plus 60, which is like 180. Since this is a negative sense, we'll have negative 180. Taking it to the other side, we'll have positive 180. And this is equation number 1. Once you have this equation, remember, global equilibrium check doesn't just involve forces, it also involves moments. So now we sum the moments, taking the moment at the point where we have a lot of reactions, which is at support A. So sum of all moments at A, taking this sense to be positive, should give us what? 0. Remember, engineers have the best moment. So let's try and find them. So from A, moving towards B, if we put a hinge at A, let us now see how many turning effects we'll have. Now from A, moving at the dimension of 2, we have the first turning effect caused by the 120 downwards, which is in the opposite direction of our positive sense. So this means that we have minus 2 times the force, because remember, moment is force times distance, or rather distance times force. So we have that. The next moment will be at position starting from A, moving to the point load that has been found, which is 60. Now we need to calculate the span from A to the turning effect, which is at 60. So the turning effect 60, this span from A to that point is why we just add this value 3.33 plus 2. So 3.33 plus 2 will give us 5.33. So since it's going in the opposite direction of our positive sense, it will be minus 5.33 times the magnitude of the force, which is 60. Now the next force is the force created by the support at B. So we need to say the span from A to B will be the span of the entire structure, which would be like 4 plus 4, because it's from A all the way to B, like that. Creating a turning effect in the positive sense. So we say plus 8 times by, which is basically just 8 by, and this is equal to what? 0. If you apply algebra for this sense here, what we intend to have should be about the value of 5, negative 5, 5, 9.8 plus 8by, and this is equal to what? 0. So we have 8by being equal to 9.8, and we know we have to divide this by 8 divided by 8, and in the sense we have by being equal to, now if you calculate properly here what our value should be, if we add all these values together, what are we going to end up having? So if we add just a quick check, checks are quite important when solving, so always be with your calculator. So we're having negative 2 times 120, then we have minus 5.55 times 60, then we, that's that. We have a value of 559.8, and this 559.8 divided by 8 should give us a value of 69.97. So we're having a value of 69.975, correct, 2 decimal places. We expect to have 69.98 kilonewtons, and this is the value of by. Now, we're not really necessarily done with the values of the reactions. We have by, but in the actual sense, we're supposed to find as well the reaction at A in the y-axis. So looking at equation 1 that we made here, we can use this equation to calculate the value of AY. So from equation 1, we know that AY plus BY is equal to 180. Therefore, we're having a value of by being 69.98. So ay is equal to 180 minus by, which tells us this is 180 minus 69.98. Therefore, we say that ay is going to be a value, if we punch that, of 110 kilonewtons. So we have 110 kilonewtons as our final answer. All right, don't forget, every time you're solving such questions, always remember to apply everything that I've said and check you're working correctly. All right, so thanks for watching. This is Engineer Hussein Mosapi. And remember to strategize before becoming a statistic, and let's try and push for that A+. And remember, the aggregation of marginal gains, which was the philosophy of searching for a tiny margin of improvement, is everything you do. So always practice these problems on a daily basis. All right.